Okay, so I guess now it's the good time to start. So welcome everyone in the second part of the workshop powered by Arango database, NVIDIA Triton inference server, and PyTorch geometric library. In this workshop, we will investigate the key aspects of three technologies in detail, starting from Arango database, which is a scalable, fully managed graph database, document store, and search engine in one place. The second one is NVIDIA's Triton inference server, which is an open source inference serving platform. And in the last section, Chris, I'm getting some.
Yes, I'm here.
Yeah, I guess your mic is on and I can hear some of your voices. Is it?
Okay. I will mute just in case.
Okay, cool. Thanks. Yep. And I was talking about this NVIDIA's Triton inference server, which is an open source inference serving platform. And in the last section, we will study the core concepts behind the graph sage, an inductive graph representation learning algorithm. And at the end, we will have a hands-on session where we'll exploit the full potential of graph machine learning using Triton and Arango database. So this will be a long workshop. So grab a cup of coffee and let's get started. But before getting started, so please install these downloads first. It could take some time and this will help you to have a proper sync with me during the hands-on session. So Chris, can you just paste these links in the chat section? Yep, and the agenda of the workshop will be, so in brief, this will be our agenda. We'll start with an introduction study of Arango database and Triton inference server. After that, we will cover a section in which we will discuss the importance of graph data structures and where to find them in real-world applications. This will be followed by applications of graph machine learning from various perspectives. Next, we will shed some light on the Euclidean versus non-Euclidean space. Subsequently, we deep dive into the comprehensive case study of graph sage algorithm. At the end, everything will be concluded by the hands-on session where we will build a complete graph machine learning application, starting from training a model to deploying it on Triton server and then performing Amazon product recommendation with Arango database AQL query language. So this is me. I'm a graph machine learning research engineer at Arango database. My role is to build intelligent products / machine learning pipelines / open source contributions using thorough research and engineering in the area of graph machine learning. Before joining Arango database, I was working at Define Media as a machine learning scientist and engineer, where I built machine learning pipelines from scratch. So during my academic time, I did a lot of projects / research work in the German Research Center for AI, mainly in the computer vision and graph neural networks domain. Therefore, I get the best of both the worlds, that is from the academia and industry. I'm also fond of writing blogs on AI and machine learning in production. So on the right-hand side, you can see some of my blogs. So that's a little introduction about me. Joining me today is Chris, who is our developer relational engineer at Arango database, and he will cover the Arango database section, and the rest of the sections will be covered by me. Now, handing over to Chris.
Alrighty, thank you. And 1 second here, and I'll go ahead and start screen sharing. There we go. All right. Yes. Hello. As you said, my name is Chris Woodward. I'm the developer relations engineer here at ArangoDB, and my section will be pretty brief. Just going to go over basically what is ArangoDB. Here's just a little bit about me. I'm on the ArangoML team with Sachin, as well as I cover a lot of the training and getting started with development for ArangoDB for both the community as well as people just in general getting started with ArangoDB. So if you have any questions or suggestions on getting started with ArangoDB, feel free to reach out to me through my Twitter or, of course, in the community Slack, the chris.arangodb. And I'm usually running through the various channels. So if you have any questions on that or feedback, please definitely feel free to reach out. So for my part today, we'll just take a look at what is ArangoDB. This is really targeted at people that just aren't familiar with ArangoDB. I won't be going super in-depth. This just will hopefully serve as a brief intro to everything that ArangoDB is. And if you'd like to learn more, definitely check out ArangoDB.com. We have a Learn portal through there, as well as a number of interactive Python tutorials that both Sachin and I and everyone kind of at Arango has contributed to. So it covers a wide range of topics there. But yeah, so ArangoDB, we call it the first native Beyond Graph database. Started as a company in 2015. We originally were located out of Cologne, Germany. Now I have a headquarters in San Francisco. We are an open source database under the Apache 2.0 license, but we also have an enterprise edition license. Right now, this is at the 65 plus, and really we should update this because that number is just rapidly increasing. And also, we are actively hiring a lot of developers as well. Specifically of interest to some on the call would be a currently open Python position, a senior Python developer. So if you are looking for something like that, definitely feel free to check out our website for all of our job listings. We have well over 11 million plus downloads. And well over 600 plus production installations that we know about. And then, of course, a really, really awesome number for us is the 12,000 plus stargazers on GitHub. As we are an open source database, we are, we have been supported by our community since day one. So definitely happy to see that we have such a high number of stargazers there. And if you do end up liking ArangoDB, we'd always appreciate a star, or we are a leader on G2. So if you'd like to leave us a review on G2, we always appreciate that. And yeah, as I said, we are a graph database leader on G2, highest rating for support on Gartner, and DB Engine's top 10 in all of our supported data models. And we'll take a look at some of those data models right now, actually. So ArangoDB as a native multi-model database means that we support natively multiple data models. And we really kind of like stick to this native idea because some other solutions try and like tack on or kind of like plug in support for other data models, but that doesn't really come with any of the benefits of being a native multi-model database. So we support document, key value, and graph data stores at the core C++ level. This means that it comes with a single source of truth, a single query language, that's AQL, the ArangoDB query language, that allows you to run queries against, for the different data models all within one single query. You can support all or one of these data models however you choose. The flexibility is always there, and the idea is to support this polyglot persistence idea, which is just using the right tool for the job. And with a native multi-model database, that means you can use one tool for a lot of different jobs that maybe would normally require multiple different databases. And all of this is scalable. So we are a scalable graph database. We have been for a long time, and that's something that we can do very well for each data model. We also have a built-in full text search engine, Arango Search, which I'll briefly touch on in just a few slides. We also have built-in iterative graph processing with Pregel. We currently have a number of built-in graph algorithms that you can run, but we also have support for an experimental feature for creating your own custom algorithms to run. And something that will be especially relevant to this talk is that we have ArangoML, which is for GraphML and analytics. And this comes with a number of tools for things such as with Arango Pipe for gathering metadata throughout your entire machine learning pipeline, along with a number of adapters such as NetworkX, DGL, and as we'll see, integration for services such as NVIDIA, the Triton server. We also have a Kubernetes integration with kuberango, which serves as the backbone for our managed service, Oasis. Oasis is our cloud managed platform, which supports all the major providers such as Azure, AWS, and Google Cloud. And so that's the high level view of a lot of the stuff that's covered within ArangoDB. And of course, the main benefit of doing all of this is that you get that single source. You don't have to worry about data consistency. You reduce the need for specialized developer knowledge as they can learn one database. This, of course, comes along with less maintenance and faster performance without having to do all these hops between different databases. So that's going to be a really, really quick kind of like elevator pitch version of ArangoDB. This is a quick look at the data model. Our document collections are support full JSON documents. And so as you can see, this is sort of a comparison between SQL and AQL. So being table to collection, row to document, column to attribute. So if you're familiar with NoSQL databases, that's what we support in comparison to SQL. And finally, this is a view of our graph viewer and the web UI that comes bundled with ArangoDB. This can run natively and allows you to visualize your data in a different way. You can create graph definitions to view this sorts of data, or you can also do what are called anonymous graphs, where maybe you don't know the edge collections that are required to make up your graph, and you can define that on the fly. So this kind of ties into the idea of having these flexible data models where maybe you just start out with a document store, but then you realize that you actually do have these relationships that you'd like to define amongst your data. And you can do that by defining these edge collections that show, for instance, in this scenario, we have this ax in. So we're showing this is an actor, or these are all actor nodes that connect to this movie, Devil Wears Prada, to indicate that this actor acted in this movie. And you can have more edges that go out to define further, like this movie's relationship to the genre that it's in, and these sorts of things. And we've got a large number of tutorials and stuff to help you get started with this concept. If you're just new to graph databases, and then furthermore helping clarify this idea of graphs inside of a multi-model database. This is a quick look at our query language, again, compared to SQL. The main idea behind AQL being that it's a common query language for all of the data models. That was really the main motivator of us needing to make another query language, is that natively, a lot of things only support either graph traversals or document lookups, or more on the key value. And even on this idea of having Arango Search, our search engine, this all needs to be natively supported in the query language, not something that feels added on or unintuitive. And so it is the same language across all clients regardless of the programming language you're using. You can always use AQL in it. And we like to think it's easy to understand, and the main aim being human readable. And so this is, for example, this is sort of what a graph traversal looks like. We have built-in support for multiple different graph traversals, such as shortest path and k-shortest path. And this is something that we're always adding whenever we add a new feature. It always has, first-class support in our query language. So moving on to look at Arango Search. As I mentioned, Arango Search is our built-in full-text search engine. It is natively integrated full-text search that does support all ArangoDB data models. The general view of Arango Search is what we have here. And this allows you to do text transformations to your data on insertion. And this actually supports fully federated search across multiple collections. So rather than needing to do a query against each individual collection, you do the query against a single view that unifies these collections and automatically perform some of the text transformations that you might be interested in. And just like in a normal AQL query, you can run your normal filters and filter out results, but then you can also get ranked results. We support BM25 and TF-IDF ranking, and this allows you to do sorting and things like that based on the actual relevance of the results, rather than just getting pure filtered results. There can be this sort of contextual ranking and sorting that you can do, such as with our suite of Levenstein distance tools that allow you to have this sort of like fuzzy search capabilities. All of this comes built in, and again, is natively integrated at the core level. And again, this is a sort of a quick overview, but this is showing using Arango Search within a graph traversal. So we start out with searching one of our Arango Search views with a string of keyword searches that can find relevant results based on movie descriptions. And we can even do things like boost, like for instance, here we're boosting the term galaxy. So we want these like sort of sci-fi, as you can see based on the keywords, sci-fi relevant results that specifically focus on the galaxy keyword. And then we can do a graph traversal based on the results of our full text search and find relevant results based on that. So a lot more of this information available through our website. We have multiple Python notebooks, Jupyter notebooks, as well as full courses that can take you through getting started with Arango Search and graph traversals. Part of the enterprise side of this is that ArangoDB, of course, the enterprise edition offers enterprise-grade security. We have full encryption for TLS, encryption at rest, encrypted backups, as well as a number of access control and auditing features, disaster recovery, data replication, and all of this worth calling out is that all of this support also is available through our Oasis. Actually, not available. All of the Oasis deployments utilize these security features. And if you'd like to learn more about that, definitely look into our enterprise server through our website as well. And finally, this is Oasis. Fully managed, fully programmable, and like I already mentioned, supports the major cloud providers, and actually has a free to try option as well for 14-day trial. And we have announced that we've got developer deployments coming as well for quick prototyping and these sorts of things that offer a cheaper way to get started with ArangoDB in the cloud before moving to production. And finally, the last view is going to be with ArangoML. ArangoML is our suite of tools that we offer to make working with machine learning and ArangoDB a lot easier, and then to provide extra value in the form of having Arango pipe be this extensible metadata layer that you use across your entire machine learning pipeline. It serves as a drop-in that allows you to gather this metadata for each step, regardless of the libraries or frameworks that you're using throughout your Arango or throughout your machine learning pipeline. We have things such as NetworkX support, DGL. We even have a notebook showing on how to use Arango pipe within just TensorFlow, PyTorch, and just to show how easy it is to drop in to whatever tools you're already using. We offer ways for simply to allow for ingesting data with the tools you're already using. And that's where some of our callouts that we have here. And this is also open source. You can go to the GitHub ArangoML organization and see all of the repositories and projects that we are working on or have already made available for release, as well as their own Jupyter notebooks to show getting started with them. And as I mentioned before, Pregel, we do have Pregel support natively into ArangoDB, and we've got this custom Pregel. So if you'd like to try out seeing what custom Pregel or just using Pregel, the built-in Pregel algorithms such as PageRank, and that's natively supported and available. And we have documentation as well as tutorials available here. And we'll share all these slides as well, so you can get access to all these links that we have noted in the slides as well. And finally, as I mentioned, just kind of taking a full view of ArangoML and where it fits in. The benefits of using a multi-model for machine learning. And if you are more interested in this idea of machine learning, gathering machine learning metadata, Arango Pipe is definitely where you want to look. We have the ArangoML pipeline cloud that allows you to utilize ArangoDB Oasis for this entire process as well, and a lot of notebooks that actually utilize ArangoDB Oasis for the machine learning experiments and gathering the metadata throughout that process. And we also kind of covered this idea in part 1 of the workshop. And I think for the most part, that will be everything that I cover today, but I wanted to take a quick look at the Q&A. Looks like Sachin has been on top of answering those already. So if anybody has any questions or anything like that, now will be the time. Otherwise, I'll go ahead and hand it off to Sachin. Okay, looking pretty good here. So I will go ahead and stop sharing, Sachin, and hand that off to you.
Just a second, I'll share my screen quickly. Okay. So thank you, Chris, for giving great introduction to Arango database. Now let's shift our gears towards the Triton server. So starting with the main question of why do we need NVIDIA's Triton inference server? So this server is an open source inference serving software that simplifies inference serving for an organization by addressing multiple complexities. Number one is that the thing which attracted me the most about the Triton server is that its capability to host or deploy trained machine learning models from all the major frameworks like TensorFlow, TensorRT, PyTorch, ONNX, Caffe, or even your custom framework backends. In addition to this, deployment of the models could take place in any of your favorite cloud providers like AWS, GCP, Azure ML, or even local storage on any GPU or CPU-based infrastructure. Therefore, it provides AI researchers and data scientists the freedom to choose the right framework for their right projects. The another key aspect of the Triton is that it runs models concurrently on GPUs to maximize the utilization. It supports CPU-based inferencing as well and offers advanced features like model ensemble. For example, the use cases that requires multiple models to perform end-to-end inference, such as for autonomous vehicles or conversational AI. This basically helps developers to bring their models to production rapidly. It is also available as a Docker container. Therefore, Triton integrates with Kubernetes for orchestration and scaling and is a part of Kubeflow. It exports Prometheus metrics for monitoring and can be used with cloud AI platforms like Google Cloud platforms or Azure ML. Therefore, you can say that it helps the IT or DevOps or ML ops engineers to streamline model deployment in production. It supports the standard HTTP gRPC interface to connect with applications like load balancers, and it can easily scale to any number of servers to handle increasing inference loads for any model. Therefore, Triton can serve tens or hundreds of models through Model Control API. So this is how a Triton inference server architecture looks like with its various connected components and the functionalities which it supports. We'll start with creating an AI model repository in which we can place our deep learning models with their respective configuration files. Afterwards, we load this repository on the Triton server in order to start serving these models on a single GPU or on multiple GPUs. As models are retrained with the new data, developers can easily make updates without restarting the inference server or disrupting the applications with the help of various polling modes. Once the Triton server is started with all the models, we can start sending the inference request for our input data to the hosted models and receive back the predictions or embeddings depending upon the use case. So these inference or query scripts can be written in client applications using Python and C++. So this is the model configuration file, basically how it looks like. This model configuration file basically contains the details of all the permissible input or output types, shapes, and favorable batch sizes, versionings, platforms. Since the server doesn't know the details about these configurations, therefore we write them into a separate configuration file. On the right-hand side, you can see a typical configuration file from a Hugging Face transformer model, which is basically expecting two inputs for inference of these dimensions, and it will output the embeddings or the predictions basically with this output dimension. So these kinds of requirements about the models, like what kind of input it should accept and what kind of output it should give, we given beforehand to the Triton server. So now let's deep dive into the graph machine learning universe, like which is really excited for me. I've been doing a lot of things related to graphs now recently. So why graphs are fantastic and where we can actually find them. So according to the Gartner top 10 data and analytics trend for 2021, as many as 50% of Gartner client inquiries about the topic of AI involving a discussion around the use of graph technology. About why the graphs are fascinating, we can answer these questions in a few parts. For the first one of the things which makes the graph fascinating is its ability to connect isolated data points in space, which is, however, missing in other forms of data representations like 2D grid structures used to represent image pixels, 1D sequences used for text, speech, or time series. Second one is that the graphs allow us to store relational knowledge among interacting entities. That is how different set of entities are related to each other based on some measure. So all the aforementioned representations like 2D grid or 1D sequences, except the graph, lies in Euclidean space, that is a regular unstructured data. And we all know that the well-known method to extract meaningful patterns from the data in Euclidean domain is convolutional neural networks. However, in real world, we are also surrounded by graph data, for example, Internet of Things, 3D point clouds, social networks, event graphs, where nodes represent the real world entities and edges are associated with relationships between those entities. So graph as a unique non-Euclidean data structure cannot be operated by CNNs, therefore require a special method to handle its non-regular structure, which basically led to the recent progress in the area of graph neural networks. So in the machine learning universe, graph data structures are exploited by graph neural networks to perform the task of node classification, link prediction, graph classification, or even clustering. So in the couple of slides, we will see some of the interesting applications of graph machine learning, starting with the number one is the scene graph generation. So the current state-of-the-art object detection models like YOLO or RCNN, what they does is that they localizes one or more objects in an image by drawing bounding boxes around them and then classifies these localized objects into one of the several classes. For example, in this image, the object detection models will understand the scene by okay. Will basically understand the scene by just detecting two objects in it. So which will be horse and man. However, the semantics of the image is totally different, which is basically a man is feeding the horse. So this kind of information cannot be gathered from this object detection models like YOLO or RCNN. So to overcome this limitation, scene graphs can be used, which can be explicitly model objects and relationships. So what they do is that given an input image, scene graph can generate a visually grounded graph in which the nodes of the graphs are represented by object instances. And in image and the edges here, you can see that this shows the pairwise relationships among the objects instances. The another area where the graph machine learning has made an impact is traffic prediction. Researchers at DeepMind have partnered with Google Maps team to improve the accuracy of real-time estimated time of arrivals by up to 50% in multiple countries by using advanced machine learning techniques, including graph neural networks. Oh, we are, I guess, hitting with some of the messages. Okay. Okay. So Chris is answering. Oh, cool. Yes. So the other important application is this visual recommendation by Pinsage. So the company known as the Pinterest, which is a platform in which they share and organize images, develop the Pinsage algorithm, which is another variant of GraphSage and uses a random walk-based GraphSage algorithm capable of learning embeddings for nodes in web-scale graphs, which basically contains billions of objects. So Pinsage is mainly used by Pinterest for visual recommendation by combining both visual, textual, and graph information. The other interesting application which I recently came to know about is the particle physics. So this is an image of CMS detector at the Large Hadron Collider, which produces complicated images of particles generated from collisions. Scientists there are using graph machine learning to study the particle interactions of interest. So food discovery with Uber Eats uses the power of graph machine learning to suggest its users the dishes, restaurants, and the cuisine they might like next. To make these recommendations, Uber Eats uses the GraphSage algorithm because of its inductive nature and the power to scale up to billions of nodes. And this David Bieber from the Google proposed an architecture to combine the advantages of graph neural networks and recurrent neural networks and called it as an instruction pointer attention graph neural network. So the aim of this architecture is that basically to imitate the structure of the interpreter and explore the close relationship with the models. So if the figure basically shows you that the model path comparisons, the edges in these graphs represent a possible set of paths along which information may propagate in each model. The pills indicate the positions where these pills basically indicates a position where a model makes a learned branch decision. So what authors have stated that after training step, this graph neural network can generate discrete branch decisions most of the time, and in fact has learned to execute by taking shortcuts using fewer steps to execute programs than used by the ground truth trace. The last application which we observe is the prediction of drug target interactions from the life sciences domain, which is an important part in drug discovery and repositioning. Drug repositioning is the method where we investigate the unseen outcomes of existing drugs, except for the original indications for medical treatment. So efficient predictions of drug target interactions can improve the robustness of drug clinical trials, which decreases the risk of experiments. Hence, the author proposed this new method called large-scale graph drug target interaction to predict these interactions based on large-scale graph representation learning, where this algorithm can extract the local and the global structure information from the graph, and at the end, two sets of features are given to the random forest classifier to train and predict the probable drug target interactions. Oh, more questions are coming. Let's see. Okay. So now, what is basically graph? So if we want to understand graph in a very easy manner, then graph is basically a data structure made up of nodes or vertices and edges. So edge describes a relationship between the two node entities based on some measure. We can define it, this graph, mathematically as G is equals to V and E, set of basically vertices and edges. So in this slide, we will see that how the machine learning was applied on graphs traditionally. So traditional machine learning on graphs follows standard machine learning pipeline to extract structural information from the graph. So we start by extracting some graph statistics or features from graph, for example, node degrees, clustering coefficient, deep walk features, Laplacian metrics, etc. So in this case, we are extracting the node degrees from this graph. And once these node degrees are extracted, we can use these extracted features as input to our machine learning classifier, example, SVM or logistic regression. Yes, but there are some caveats of these traditional machine learning approaches. The caveats here are that these approaches are restricted since these hand-engineered features are inflexible, that is, they cannot adapt during the learning process, and designing these features can be time-consuming and could be an expensive process. Like you can think this is as of like when there was early stages of computer vision where the researchers were designing multiple filters to extract the images from to extract the features from the images. For example, like you can think of that a filter which basically extract all the edges from the images. Then they were designing another filter which basically extract more high-level features like the nose and eyes of the face. And yes, but designing those features with the hand was really a very cumbersome approach. And then the CNNs came into the picture, and what CNNs does is that they started like learning these filters or these kernels automatically via the stochastic gradient descent process. So this basically comes to the next question, that can we apply convolutional operations on graphs similar to images to automate feature learning? We know that the convolutional neural networks are designed to operate on regular fixed size data structure, or you can say that data structures which can be represented in Euclidean space. Let's understand this term regularity in data structure with the help of this cat image. Images can be seen as a special type of graph known as the grid graph. Now, applying convolution in this case means that we examine the neighbors of each pixel by aggregating their values. For example, this red pixel is aggregating the features from its immediate surroundings. So one thing to note here is that each pixel in this 2D grid is surrounded by a fixed number of neighbors. So if we move this window from left to right or from top to bottom, the neighborhood size of a target pixel remains the same. However, if we move into this non-Euclidean domain or in the graph domain, the neighborhood size of a target node varies. For example, in a social network graphs like Facebook, a very popular person could have millions of connections or neighbors, whereas the normal one can have a very few connections. Also, the another important thing to note here is that in 2D grid, there is a fixed ordering of neighbors, whereas in the graphs, the order of neighborhood of a target node is arbitrary, and this property is also known as sometime permutation invariant. So graph convolutions, they're also sometimes known as the message passing neural network. So in the graph convolutional neural networks, the convolution, so then the question here is that, like, how then we can perform the convolutions on the graph. Then the way which left with us is basically how we can apply these convolutions on the graph is that these convolution-like operations, we can represent them as a two-step process, that is aggregate and update. So we aggregate the features from the neighborhood of a node and then update the target node features with these aggregated features. So for example, in this diagram, you can see that how all of these nodes are aggregating features from their neighborhood. For example, like this node M5 is pulling out the features, or it's like asking its neighbors that please provide me your knowledge, or provide me what actually you knows, or provide me your features. So once it aggregates these features, so M1, M2 messages from these their corresponding neighbors which are at first hop. Once the node features are aggregated, we update them with the help of all the aggregated features as well as its own features. So here, as we have seen, the limitation of applying traditional machine learning on graphs is that the hand-engineered features are inflexible. The next question comes into mind is finding a way to integrate the information about graph structure. For example, information about the node's global position in the graph or its local neighborhood structure into a machine learning model. So to tackle this problem, representation learning approaches have been adopted to encode the structural information about the graph into the Euclidean space. So how we can do this encoding? So the key idea behind this graph representation learning approaches is that to learn a mapping function that embeds nodes or entire subgraph as a points in a low dimensional vector space to embedding space. So this is the idea that the nodes which are very close in the network should also remain, when we perform this or when we learn this mapping function, the node should also remain very close in this dimensional space. So the key idea behind this graph representation learning is to learn a mapping function that embeds nodes or these entire subgraphs so that to optimize this mapping so that the nodes which are nearby in the original network should also remain close to each other in the embedding space while showing the unconnected nodes apart. Therefore, by doing this, what we are achieving is that we are preserving the geometric relationship of the original network inside the embedding space by learning a mapping function. So this is the similarity function you see, and this basically shows you the similarity between the two nodes in the network, and this is the dot product between the node embeddings in the embedding space. So these two are the two components. So the two key components here are, the first one is the encoder, which maps a node to a low dimensional vector. Second one is the similarity function, which defines how the relationships in the input network map to the relationships in the embedding space. Here, the similarity function could be, for example, the cosine or Euclidean distance, depending upon his or her choice. So that was all maybe kind of much more mathematical definition. To understand this more intuitively, we can understand this with an interesting example from the graph structure of Zachary Karate Club social network. So if you see this graph, the nodes basically represent the persons, and there exists an edge between the two persons if they are friends. So the coloring in this graph represent different communities. If you see the figure A, basically represents the Zachary Karate Club social network, and figure B illustrates the 2D visualizations of node embeddings created from the karate graph using a deep walk, which is one of the graph representation learning methods. So if you analyze both of these diagrams, you will find that the mapping of nodes from a graph structure, basically from diagram A to diagram B, or from graph structure to this Euclidean space, is done, or this mapping is learned in such a manner that the distance between the nodes in the embedding space mirrors closeness in the original graph. That is, they are preserving the structure of the node's neighborhood. For example, if you observe the community of the people marked as violet and green, which shares a close proximity in the 2D space as well, if you observe these two communities, you will see that after the encoding function is learned, this proximity is also being preserved in the 2D space as well. Similarly, if you observe these violet and sea green nodes, which are very far away in the network, so this kind of behavior you can also observe when the mapping is performed in the 2D space, or when encoder learns this neighborhood structure, and it is basically preserving the neighborhood neighborhood structure of the nodes. So what can we do with these embeddings? So once these node embeddings are learned, we can use these embeddings for various machine learning downstream tasks. It can be used as a feature inputs for number of downstream machine learning tasks like community detection via node classification or link prediction. We could construct a KNN or k-nearest neighbor or cosine similarity graph from embeddings. And then that graph could be used to make recommendations, example, product recommendation. Then the visual exploration of data by reducing them to 2 or 3 dimensions using the UMAP or Tisney algorithm. So this third one, basically the visual exploration by UMAP, we will do in this workshop during the hands-on session. And then the fourth one is we can also do a dataset comparison and then the transfer learning. Now coming to the GraphSage part. So a GraphSage, we will cover basically GraphSage algorithm in detail in this workshop, which is an inductive algorithm. So here with the word inductive, it means that it can generalize to unseen nodes. And this method is developed by Hamilton, Jing, and Leskovic for graphs used to generate low-dimensional vector representations for nodes. So this is in contrast with the previous graph machine learning methods like graph convolutional networks or deep walk, which are inherently transductive. So transductive means that they can only generate embeddings for the nodes present in the fixed graph during the training. So if in future the graph evolves and the new nodes takes their place into a graph, then these traditional graph convolutional methods or the deep walk methods need to train the whole graph again in order to learn the node embeddings for this newly added node. The other main limitation of transductive approaches, mainly deep work or not too weak, is that they cannot leverage the node features, for example, text attributes, node profile information, etc. On the other hand, if we see the graph search algorithm, it basically exploits both the rich node features and the topological structure of each node's neighborhood simultaneously to efficiently generate representations for new nodes without retraining. So the working principle of graph search is mainly divided into two steps. The first one is performing neighborhood sampling of an input graph. And the second one is learning aggregation functions at each search depth or at each layer. We will discuss each of these steps in detail, starting from with a little motivation of what was actually the need to perform the sampling of nodes neighborhood. Afterwards, we will discuss the importance of learning aggregator functions, which basically had helped graph search algorithm to achieve its property of inductiveness. To understand the importance of neighborhood sampling, we will take the perspective of graph convolutional network. So let's understand this from the lenses of the graph convolutional network. So GCN is an algorithm which can leverage both the graph topological information, that is nodes neighborhood and node features, and then distill this information in order to generate node representations or dense vector embeddings. The diagram basically represents the working process of GCNs intuitively. On the left-hand side, we have a sample input graph where its nodes are represented by their corresponding feature vectors. So these feature vectors could be node degrees or text embeddings, etc. We start, so these are the feature vectors. So we start with defining a search depth K, which informs the algorithm up to what depth it should gather the information from a neighborhood of a target node. So in this whole 3 or 4 slides up to this, while I'm explaining this neighborhood sampling or the graph search algorithm, I will consider the target node as the 0th node. So here K is a hyperparameter, and it also depicts the number of layers used in the graph convolutional networks or the GCNs, to say it in the short form. So what happens at K is equals to 0 is that, so this one, so at K is equals to 0, GCN initializes all the node embeddings to their original feature vectors. So original feature vectors, it could be a text feature embeddings or node degrees. So all of these nodes are represented by their original feature vectors. Now let's say we want to compute the embeddings for the target node 0 at layer K is equals to 1. Then what we do is that we aggregate all the feature vectors of nodes, including itself, which are at 1 hop distance from the node 0. So at this time step or layer, we are aggregating the original feature representations of nodes which are at K is equals to 0. So what we will do is that we will ask the neighbors of the nodes, which node 0, which is basically 1, 2, and 3, to give, or we will, what we'll do is that we will pull their feature vectors, which you can see it in this diagram, like what is happening after or at K is equals to 1 or after this search depth of K is equals to 1. What this node now knows is that about the information about its immediate neighborhood. So this process is basically shown in this GCN right-hand side image. Now after k is equals to 1, now it knows like what basically lies around my surroundings up to 1 hop. So we repeat this process for all the nodes in the graph. That is, for every node, we aggregate over the 1 hop neighborhood in order to find the new representations for each node at each layer. As the search depth increases, the reach of the target node in terms of aggregating features from its local neighborhood also increases. So this is how basically the GCN at k is equals to 1 works, just extracting the feature vectors from the k-1 layers and basically pulling it up and then performing a mean over these feature vectors along with its own features. But there is an issue with this approach. The issue here is that the GCNs compute node representations using the neighborhood aggregation. For the training purposes, we can represent the k-hop neighborhood of a target node as a computational graph and send these graphs in a mini batch fashion in order to learn the weights of the network, that is applying stochastic gradient descent. The diagram illustrates a computational graph for the target node 0 up to 2 hop neighborhood. Now, the problem with this is that, number one, it is computationally expensive. Why? Because since for each node, we need to generate the complete k-hop neighborhood computational graph and then need to aggregate plenty of information from its surroundings. As we go deeper into the neighborhood, that is the larger k value, computational graph becomes exponentially large. This could lead to a problem while fitting these big computational graph inside the GPU memory. The second main limitation is the curse of hub nodes or celebrity nodes. Hub nodes are those nodes which are very high degree nodes in the graph. For example, a very popular celebrity having millions of connections. So if we encounter that node in the graph during sampling, then we need to aggregate the information from millions of nodes in order to compute the embeddings for the hub node. Therefore, the generated computational graph for the hub node is very huge, which could lead to a problem, basically lead to the problem of fitting inside the GPU memory. Therefore, the idea is not to take the entire k-hop neighborhood of a target node, but select a few nodes at a random from the k-hop neighborhood in order to generate a computational graph. So this process is known as neighborhood sampling, which provides the graph sage algorithm its unique ability of scaling up to billions of nodes in the graph. So you can see in this diagram, we are not taking all of the neighbors of a target node, but are sampling at most 2 neighbors at each hop. Why graph sage is called an inductive algorithm? So as I have discussed with you that graph sage is an inductive version of graph convolutional networks, which implies that it does not require the whole graph structure during learning, and it can generalize well to the unseen nodes. Its inductive property is based on the premises that we don't need to learn the embeddings for each node, but rather learn an aggregation function. And this aggregation function could be any differentiable function like mean, pooling, or LSTM, which when given an information or features from the local neighborhood of a node, then it knows how to aggregate those features such that the aggregated features representation of a node, target node V, now includes the information about its local surroundings or neighborhood. So if you see this diagram, it illustrates how graph sage node 0 aggregates information from its sampled local neighbors at search depth k is equals to 1. So here we are just randomly sampling the node indices 2 and 3. And yep, so if we observe the right-hand side graph, we will find out that the k at the k is equals to 1, the target node 0 is now having the information about its surrounding up to 1 hop, but with the sampled neighborhood. Let's see the question. Okay, so that's a good question. How do you know which differentiable function to use as an aggregator? So this is basically a hyperparameter. Basically, the user decides which aggregator function it needs to use, and we can experiment with, depending upon the use case, we can experiment with different aggregator functions. I hope this answers. Yes. Now we will see the formal explanation of GraphSage. This basically from the GraphSage paper, variables here defined, which we need to understand before understanding this algorithm. As I have explained you that the key concept of GraphSage is to learn how to aggregate feature information from a node's local neighborhood. Now let's understand more formally how the GraphSage generates node embeddings at each layer k using the forward propagation. We understand this with the help of visuals, and then we can map this understanding to a pseudocode mentioned in the GraphSage paper. But before that, let's define some notations which are used in the paper. So for example, this x of v represent the feature vector of node v. H of v of 0 is the initial node embedding representation for a node v, which is its original feature vector, could be text or image embeddings. Then hv of k is the node embedding representation for a node v at the kth layer or the kth search depth. Then z of v will be the final representation. After iterating through all the search depth, we'll get the z of v, a final representation of node v. And then we have v is the set of nodes in the graph, and wk, this is the learnable metrics at the kth layer. So this is basically proportional to how many layers we are using. So if we are using 3 layers in the GraphSage, then we will learn the 3 different set of matrices at each layer. And then this is the neighborhood function. Starting with what's happening at k is equals to 0 is that this image depicts the computational graph of a target node 0 at layer k is equals to 0, or at the initial search depth. At this point of time, all nodes in the graph are initialized to their original feature vectors. Our aim is to find the final representation of a node 0, that is z of 0 at layer k is equals to 2, through an iterative local neighborhood information gathering process. So this iterative process is sometimes also known as the message passing approach. Therefore, we can represent this step formally as this equation. So what this equation is implying is that we are initializing each of the feature vector of node v as their original feature vectors. So 0 here means the search depth, at which search depth or at which layer we are, and the v represent the node. Here, for example, you can see here in this image that this feature vector, this is the node 0 representations, basically hidden layer representations. So h here is mean the hidden layer representation of node 0 at 0th layer. So this means that what is the hidden layer representation of node 2 at 0th layer, similarly hidden layer representation of node 3 at 0th layer, they are all represented by their original feature vectors. Now what will happen at k is equals to 1 is that since node gathers the information incrementally from the deeper depths of the graph, we start our iteration process from search depth 1 till k is equals to 2 for this demonstration purposes. At k is equals to 1, we aggregate neighboring node representations for our target node 0, which will be 1 of h of 0, which means that now we need to compute the representation of node 0 at layer 1, and 0 is the index. So similarly, we will also compute the representation of node 2, h of 2, hidden layer representation of node 2 at layer 1. What we are going to do in this step is that, for example, for this target node 0, we need to get the node second and third represent node index 2 and 3 representations, which were at the previous layer, that is k minus 1 layer. So we basically pull the feature vectors or the node representations from the one previous layer, basically the k minus 1 layer, and we combine those representations into a single vector. So here 1 of h of 0 is an aggregated representation. At the same time step, nodes 2, 3, and 9 will also aggregate the feature vectors from their respective local neighborhoods up to a distance of 1 hop. Now, at this point of time, each of the nodes in the computational graph knows what kind of information lies in their immediate surroundings. So the neighborhood aggregation step could be defined by this equation, which basically means that for every neighbor, what we are doing is that we are taking the neighborhood of a target node. So let's say, for example, 0. So v, n of v basically represent the v could be here 0, and we are taking all its neighbor. So its neighbors are 2 and 3, and then we are selecting their k minus 1 representation, the representations which were before this search depth. That is basically these representations at search depth k is equal to 0. So we are basically getting these representations, or pulling these representations from the pulling this k minus 1 representations of node from the neighbors of a node 0, and then what we are doing is that we are aggregating it. So as I told you, that the aggregation could be here any differentiable function we can use to aggregate this representation. We can use addition or LSTM or even pooling. And then once it is aggregated, we can represent this whole aggregated feature representation or node 0th representation as h of k n of v, basically this one, the node representation, hidden layer representation of node 0 at the first layer. So once we have this aggregated representation, now what we need to do is that we need to update this final representation of node 0. So updation here means that we basically concatenate basically we concatenate the neighbor representation of previous layers of node 0 to this to its with self representation. So this basically depicts the neighborhood information of the node 0, all the previous representations, and then we are combining it with the current representation, sorry, not the current one, but its original representation, like what it's being shown over here. And then we are taking a dot product between the weight matrix at this layer, which is basically the k is equals to 1 layer. And then afterwards we are applying a sigmoid function which will transform the output, making it capable to learn and perform more complex tasks. The important note here is that the graph sage learns the weight metrics individually at each search depth k, or you can also say that it learns how to aggregate information from a node's neighborhood at each search depth. At the end, once we have these updated representations, after pulling the k-1 representation from all the neighbors, we update the representation of nodes with its own representation, and then we can basically normalize this representation by taking the L2 norm of the representation of the node 0, let's say. So this is basically a comparison between how the neighborhood aggregation is taking place between k is equals to 1 and k is equals to 0. What we are doing is that, so let's say we are computing the new representations of node 0 at k is equals to 1. We are just pulling the feature representations from the immediate neighborhood nodes, and then we are updating it via performing the concatenation with its own representation, and then applying the sigmoid, and then normalizing the final representations. So yeah, this is how we get the representation at k is equals to 1. And at k is equals to 2, what happened is that the information gathering from nodes local neighborhood at k is equals to 1 is completed now. And at k is equals to 2, nodes explore the further reaches of the graph, that is going beyond their immediate neighborhoods and looking into a hop distance of 2. Again, we perform the node's local neighborhood aggregation, but this time the target node 0 will now have the information of its neighbors, which are at 1 hop distance and 2 hop distances. Then again, we repeat this process of updation and normalization for each search depth k is equals to 2. Since we have set the value of k is equals to 2 for understanding the flow of the graph sage, therefore we will stop here. And after k is equals to 2, each node in the computational graph is represented by their respective final node embeddings, that is z of v. So at this point of time, now the node 0 is having the information or its nodes, its local neighborhood up to 1 hop and up to 2 hop distances. So yeah, so as we go into the deeper depth, more and more information the nodes basically gathers about like what surrounds them. So in this slide, we are comparing the node representations or embeddings at each layer of the graph sage. As the search depth increases, the reach of the target node in terms of aggregating features from its local neighborhood also increases. For example, at k is equals to 1, the target node knows the information about its local neighborhood, which are at 1 hop distance. At k is equals to 2, the target node knows the information about its local neighborhood, which are at 1 hop distance, and the neighbors of the nodes of 1 hop distance, that is up to 2 hop distance, that is neighbors of neighbors. Now this you can visualize this with the help of this comparison between the representation learning at each search depth of graph sage. So since now we have an understanding of how the graph sage works, or how basically the forward propagation or this feature aggregation from the neighborhoods are performed, it will be easy to map our understanding to the given graph sage problem. So we start by defining the graph, the input features, the depth, the weight matrix, this non-linearity function, differentiable aggregator, and this neighborhood function. So first, again, we start with, as we have seen, that we start with the initial representations of the node, that is their original feature vectors. Then we iterate over all the search depth. And then for each search depth, what we do is that for every node in the graph, we compute its representation at each of the search depth. So for every node, what we do is that we aggregate the features from their neighborhoods, and then we concatenate with its own features, which are at k-1 layer, and then we normalize them, and then we repeat the process again for the search depth 2, and then again for search depth 3, going beyond and beyond into the more deeper neighborhoods of a target nodes. So at the end, we get the final representations of the node, which is basically represented by Z of V. So the loss function here we use for the training purposes is that in the case of supervised learning, the author uses regular cross entropy loss for performing the task of node classification. In the unsupervised case, as we have discussed, that the aim is to optimize the mapping so that the nodes which are nearby in the original network should also remain close to each other in the embedding space or vector space, while pushing away the unconnected nodes apart. So they have used this graph-based unsupervised loss for this to achieve or to learn this encoder function. Okay, so here right now we okay, so this question is being asked, is always the same number of nodes being aggregated at each kth layer? That's a good question. So let's just get back to that slides where maybe it could be helpful to explain this question. So actually, the question basically asking that is if it's the same number of nodes being aggregated at each kth layer. So the answer here is that no. So we can basically define this is basically a hyperparameter, and we can define this thing. So for example, if you will see in the upcoming this hands-on session where we will define that where we are going to use this graph stage algorithm, and there we perform the neighborhood sampling of the whole graph up to 3 layers or up to 3 search depth. And in that, what we will do is that for the first layer or for the first depth, we are going to use, or we are going to sample the 15 neighbors of a target node. And then for a 2-hop distance or at search depth k is equals to 2, we are going to sample for all those 15 neighbors. We will sample for each of these 15 neighbors, we will sample their corresponding 5 neighbors, 5 or 10 neighbors. And then at search depth 3, we will select the sampling neighbors to a number of 5, let's say, and then from those selected 10 neighbors, we can select each of their 5 neighbors. So this is basically hyperparameter to try out with the different numbers of neighbors to sample at each search depth. So this could even get more clearer when I will show you the script where we will perform this neighborhood sampling. So that will make this question more clear. Okay. So this comes to a end with the theoretical part of the graph sage. Now we will shift our gears towards the hands-on session. So the outline of the hands-on session is that we will train a graph machine learning model using PyTorch geometric library. The dataset which we are going to use is the Amazon co-purchasing dataset, basically taken from the Open Graph Benchmark library. Then afterwards, we will set up a Triton server on a local machine. Then we will deploy this trained graph sage model on the Triton server, which is basically our first application for graph machine learning in production. Then we will write down a Python client-side script to interact with graph machine learning models served on Triton. And at the end, we will conclude by writing up this Amazon product recommendation case study, which involves Triton inference server and Arango database. A little introduction about what is how this data set is being constructed. The co-purchasing data set, it basically represents the Amazon co-purchasing network. So here the node represent the Amazon product descriptions. We are having 2.4 million nodes, and the edges between the two products indicates the products purchased together. So whenever the two products are purchased together, there is a edge between, or there's the edge is constructed between those two products or between those two nodes. So this will be a node level prediction task where the data set is having 47 categories, example, cell phones, videos, video games, clothing, etc. So the pipeline for Amazon product recommendation case study with the graph machine learning, Triton and Arango database we are going to use is this one. So we are going to build this complete application using this pipeline. So we start with trained graph sage model, and we place it on a model repository, and then we deploy it on the this model repository on the Triton server. Once it is deployed, and now let's say I want to know the node representations or embeddings for this node 5, and yes, and then how I can know its embeddings or its representation is that we can write a front-end client application or an inference script, which basically interacts with this Triton server. What we can do is that we can, with this inference application, we request for the embeddings of the node 5, and we hit the server with all the inputs. Inputs here are basically the node 5's original feature vector and its corresponding adjacency metrics, or basically the computational graph which I have shown you previously. And then the Triton server gives back its embeddings, node 5 embeddings, and then what we do is that we update the graph, this Amazon product recommendation graph, with this newly added embeddings, because all of these embeddings which we will generate is for the test data, and the test data, as we know, that is the data which we never see during the training, and we will store the node representations for these test nodes and update the graph basically with this new node representation. So let's say as we want to get, so N5 is the test node, and then we don't know its embeddings or its representations, or we don't know its classification, product classification, like what kind of product it is. And we request for these, we request for these N5 embeddings via our client application. We get back the embeddings from the Triton server, and then we update the graph, which is basically residing in the Arango database with this newly added embeddings for the node N5. So once this graph is updated with this Node 5 embeddings, what we can do is that we can perform a graph traversal with ArangoDB's AQL query. For example, retrieve all the embeddings of the neighbors of node N5, which are at one hop distance. So what is the advantage of doing this is that with the help of this kind of query, or with the help of this kind of traversal using the AQL, we can know the surroundings of the node N5. Basically, what kind of local neighborhood it has. And the second application which we can build is that the whole pipeline will remain same, but what we can do is that once the graph is updated with this embedding for the node 5, what we can do is that we can perform AQL query, and we can perform this cosine. We can actually evaluate, or we can perform this cosine similarity between the query product and the other likely. So let's say we have this query product, and we don't know that what kind of product we can bot together with this product. And then if we have its embeddings, then with the help of the cosine similarity, we can find the similarity between all the embeddings which lies in this data with this query product, and then we can get back the topmost similar results. So this application we will see in our hands-on session. So the idea is that given a query product, please find the similar likely bought together product with this query product. And yeah, now we can start with the hands-on session. So let me move to the hands-on screen. I guess everyone has already downloaded this GitHub repo. And so since the first goal is to train this graph machine learning model, and then what we can do is that we can, so this is the notebook which I have written to train a graph search model on this Amazon product recommendation data set. So we can start by installing all the necessary libraries. So it will start installing them, and then yeah, it will take some time, and then we can import all our libraries afterwards. Or the other thing I can, so you guys can simultaneously feel free to play with this notebook. I can use my own notebook where I have already installed all the libraries, and I can just quickly show you like how we can train this graph search model on this Amazon product recommendation dataset. So let me see where it is. So kernel. So here, what we are doing is that we are basically providing the path where we need to store this data set, Amazon product recommendation data set. And then as you can see that I've already downloaded this data set for this demonstration purposes. And then we can load this data set. So once it is loaded, we can get this index split. So this is the training, validation, and test split based on sales ranking. So they have already decided which nodes will come under training, validation, and test nodes. Here we can check some of the graph statistics. For example, this one. So this is the node feature metric. So it says that represents that we are having around 2.4 million nodes in the graph, and each of these nodes are represented by their original feature vectors, basically with this much size, that is 100. So each of the node is represented by a 100-dimensional feature vector. So this feature vector is nothing but the product description. Let's say there is a node in the graph and it belongs to a home and kitchen label. And what the Amazon people does is that they took the description of that label and they have calculated the bag of word features, and then they represented this bag of word features at this 100-dimensional feature vector. And similarly, this is this data.vy represent the labels. So we are having this much, again, the labels, 2.4 million labels. So we are having labels for each node. And the second one, graph connectivity, basically represent the adjacency list, or in PyTorch geometric universe, it is known as data edge index. Basically represents that which node of the graph, which node is connected to which other node. So it's just the adjacency index, or the known as the edge index in PyTorch geometric. So these are the labels we have. We are having 47 labels. So you can see some of the labels here. So these are the node labels are home and kitchen, health and personal care, beauty, and so on, like this. And so here what I'm doing is that I'm performing the mapping. So from this, so this data set basically only contains the numerical integers, and they have provided this CSV files, which basically contains their corresponding product category to a label index. And then I am performing a mapping, and then with the help of this mapping, I'm just assigning the node integers to their product categories. And this basically shows you the count of each of the category. So for example, this category 4 has 6,000, around 600,000 labels. 600,000 categories nodes basically belongs to these labels, like this, the count, the class count, basically. We are having questions. So the question is that if this Jupyter notebook being shared anywhere, if yes, where can I access it? So yep, as I have told you, all of these notebooks are available in the GitHub repo, which we have shared in the start and also during the workshop. So you can get all of these codes there. And yeah, this basically shows you that how many nodes belongs to the training set, how many nodes belongs to the test set, and the validation set. And yep, and this is the neighborhood sampler, which I was talking about, or the question was asked that if the same number of nodes being aggregated at each kth layer. So the answer is that no, at each layer we sample different number of nodes. So it means that, so this is the neighborhood sampler graph from the PyTorch geometric. So here we define the sizes and sizes for each of the layers. So for this graph stage algorithm, we are using 3 layers, and it says that at first hop, I mean, if we want to sample the neighbor of a target node, then it says that from the first hop, sample the 15 neighbors only. So if there are 100 neighbors in the first hop, then we will sample only the 15 neighbors. And then in the second hop, we will sample for all of these 15 neighbors, we will sample for each of these 15 neighbors, we will sample their corresponding 10 neighbors. And then again, like this, for each of those 10 neighbors, we will sample 5 of their neighbors. So here the neighborhood sampling size is not fixed. It basically varies from, it can vary from, it can vary basically layer wise. Okay. And yeah, so this is the graph sage algorithm basically defined in the PyTorch geometric library. So what this algorithm is doing is that it's basically receiving, initializing this class with this input. So first input is in the number of input channels, which is the size of a feature vector, which in this case node feature vector, which in this case is 100. And then the second one is the hidden channel. So this hidden channel is the hidden channel will represent the size of a node, embeddings at kth layer. So let's say, so if you see here, the size we are mentioning here, it's the 256. So what it basically means that when we will aggregate the information for a target node from the neighborhood of a target node, then its size will basically reduced or to this dimension 256. So this neighborhood aggregation will reduce the node representation to 256 basically. So this is also again a hyperparameter, and yes, we can basically experiment with the various sizes which we want at each search depth. So let's say at k is equals to 1, we can set it to 256, and then at k is equals to 2, the size of the node representation we want is of f64, like this. And then the third input is the number of classes, which is 47, and then the number of layers. So we are using, we are building this graph sage model with 3 layers. And yes, again, so this is the algorithm here. So let's, if we run this, let's run this. And yeah, will take some time. So we start by initializing this init function. So here all the we define the number of layers, which is 3, and then we have this the convolution layers we are initializing with this torch NL module list, which basically kind of, you can think of as of like defining layers as in Lego blocks. So we append the graph sage layers in each of these con variable, starting with the first layer. So the first layer will receive the original feature vector size, which is 100, and then the output node representation from this layer will be, or from the first layer will be the 256. And then similarly, we use a loop. This will run for one time, and then again, it basically gets this 256 dimensional feature vector as an input, and then it again output this 256 dimensional feature vector. So for the second layer also, we are using this dimension. And at the end, the last graph sage layer will again receive this input size feature vector, and it will output the feature, will output the node representations of this size, which is basically the 47. So at the end, so this will be our Z of V, which will basically represent the final representation of a node. And yeah, this is the forward pass. We basically receive the, maybe I can show you here what does X means. So as I have told you, this X is a node feature matrix. So if we check the shape of this thing, we will see that there are 2.4 million nodes and corresponding 2.4 million nodes with their original feature vectors 100. So yes, and so these are the nodes, and then there are their corresponding 2.4 million labels. And yeah, we are here sending a model to a device. It could be here CPU or GPU. And then yeah, here we start training it. So let me just, we start training it. And what we pass through this model is, oh no, so this is the training script. So what we do is that we have this train loader. And so basically what this neighborhood sampling return is that, maybe it's defined here well. Yeah. So if you see this section, so what this neighborhood sampling return is that, so when you pass this all the training node indexes, it will it will return you the batch size, the node IDs of all the nodes involved in the computation, and a list of bipartite graph objects via this tuple. So it will return you this tuple, edge index, edge ID, and the size. So where here the edge index again represent the bipartite edges between the source and the target nodes. EID is the IDs of the original edges in the full graph, and the size holds the shape of the bipartite graph. So this will basically help the graph sage algorithm to know the computational graph for a specific node. For example, like what we have seen in our presentation, that we are basically computing the computational graph. So you can maybe I can quickly show you like what I'm saying. So this basically we receive this computational graph. So let's say if we want to know if you want to calculate the neighborhood of a node 0 at 2 different search depth, so this kind of computational graph we will receive with all its adjacency edge information, that which node is connected to the which node, and then how many nodes and which nodes are present inside that computational graph. So if in that computational graph, while calculating all the neighborhoods, if there are in this whole computational graph 10 nodes lies, then it basically tells you that, okay, so in the neighborhoods, after performing the neighborhood sampling, these many number of nodes lies in this graph for this particular test node. And yes, and then we can start the training here. So it might take, it will take a lot of time because we are right now on the CPU, but if you run it over here on this Google Colab, it will do it very quickly. So to save the time, what I did is that I will stop it here. So what I did is that if you see this repo, I have already stored the checkpoints here. And so I have trained this graph search model using the CPU as well as the GPU. So what you can do is that you can directly use these checkpoints, and then you can perform a trace on the graph search model. So here the next step would be to, so once the training is done, the next step is to perform the trace of this checkpoints. So the trace is basically we are performing in order to make a model, a Triton acceptable model. So this is the notebook where we are going to perform a trace on this checkpoints, which we got from our training script. Mm-hmm. Yeah, it takes some time. So for this, how we are going to perform a trace is that we will take, let's say, we will create some dummy inputs. So let's say from this test loader graph, just let me. So as I have explained that this test loader will basically, this neighborhood sampler will return you the three objects, which is basically the batch size, or three variables, node IDs. So node IDs are the nodes which are involved in the computation, all the nodes which are involved in the computation from when we perform the neighborhood sampling. So let me just quickly show you what I meant by this with an example. Okay. Yes, so what we are doing is that we are just selecting the first node from this test loader, and then we are and then we are storing their corresponding node IDs and adjacency list. So the node IDs basically will tell you that how many number of nodes are involved in the computational graph. So this basically shows you that this number 718 shows you that when we perform this neighborhood sampling at each search depth, the total number of nodes which are getting involved are 718. And and corresponding to this big computational graph, And now we need to know about like how this different nodes of that computational graphs are connected. We are actually getting this edge information from this dummy adjacency information. So we are just here for dummy purposes, we are just selecting the first test node. And so let me just quickly open this variable so that I can show you what actually it has. So it basically has, so it basically has three things. The first one is the edge index, which basically tells you, okay, which node is connected to which other node in each of the layers. So let's say we start with, so basically it gives back you these computational graph in the opposite manner. For example, this one edge index represent all the neighbors or all the nodes involved in the first hop. That is the node 1 is connected to node 0. Similarly, node 2 is connected to the node 0. And then the second edge index basically represent the information of the second layer, that like how the different nodes are connected in the second layer of the neighborhood. And then similarly this one is from the last one. So basically from the at k is equals to 3, how the different nodes are connected. So once we have this dummy adjacency, we stored all of these edge lists at layer 0, 1, and 2 separately in this list, and and their corresponding edge sizes. And then the next step is to pad. Yes, so since the trace of the model basically requires that maybe no. So what we are doing is that we are performing the trace on the model with a fixed input size. So when we perform a trace on the PyTorch checkpoints, what we require is that the input lengths should remain the same. So what we do is that we always trace it with the larger input, which we can thought could be enough for our future use cases. And yes, and for this for this data set, what I'm doing is that I'm performing the trace with this value 1000, which means that the maximum amount of neighbors we can get from the neighborhood of any node when we perform a sampling could be 1000. And then we are performing this, we are taking this value into account, and it will always remains the fix. Okay, so this one is not defined, and then okay, and yes, so this is the model on which we will perform the trace. So this is again this graph search model, and what I am doing is that when the trace is getting performed, what it does is that with that fixed input, it will store all the tensor operations. It will record all the tensor operations inside the forward pass, and it will also always gives back you the same dimensions or the same output, or the output with always with the same dimension. So for example, if we perform the trace here, and what we will get is that we are now, so at this point of time, we need to give the model this learned weights or these checkpoints. And once we give this checkpoint, we perform a trace. So this is the trace script. which takes 7 inputs. 7 inputs. The first one is the node feature matrix, and then the edge index, edge size for all of these 3 layers or up to 3 search depths. So each search depth will have a computational bipartite graph with its corresponding adjacency list and adjacency size. Since we are now using the 3 layers, so 2 for each one, which is basically 6, and then the first input corresponds to the total number of nodes involved in each of these 3 layers. And now we are padding it with up to the maximum dimension with this 1000 nodes. And so what this pad will do is that so what we have seen is that the number of nodes which are involved are in the neighborhoods in the sampling is 718. So we are padding the rest of the node with the zeros. So if I print the values, you will find out that only the first 718 nodes contains their corresponding feature values, and after 718 up to 1000, all the nodes are padded with the 0 values. So this will, when we perform a trace, this will not, the output or the embeddings will not get affected by these 0 values. And yep, this is how we perform a trace, and then we run the script and we trace it with the dummy input fixed dimension. So now the trace is completed, and then we are storing the traced model in the current working directory. So once the model is now being stored, now it's basically ready to get deployed on the Triton server. And if maybe I can show you this. So actually what Triton server expect is that you need to put that model in this manner or in this structure. So you name the model. Let's say we are naming it with graph embeddings, and then you store this model.pt in this folder, name it as 1. So 1 here represent the version of the model. So you store it here, and then you write its corresponding config file. So config file basically, as I have explained you, tell the model or tell the Triton server that what kind of input and output it should expect when we hit that model with the inference script. So if you see here, so this is the input 0, which is basically the node feature matrix. And then this one is the edge index of the first layer, or the adjacency list of the first layer, then corresponding edges, edge size of the first layer, then edge index for the second layer, edge size of the second layer, and similarly third layer edge index, third layer size. And then what we can expect from here is the embeddings of the nodes at 3 different graph edge layers. So at the first layer, as I have explained you in the algorithm section, that the output representation from the first layer will be 256. Then again, from the second layer is the 256. We will get basically the 256 dimensional node feature representation at first layer, at second layer, and at the third graph edge layer, the node representations will be reduced to this 47 dimensional, because we are having 47 number of labels in our data set. And then what we can do is that we can just apply the softmax over it to calculate the product which is having a very high probability. And yeah, this is kind of config file which we required for our graph search model. So 500, since for this demonstration, we are going to use the batch size of 1. So what we are going to do is that we iteratively gets a test node from this test loader variable, like 1 by 1. And then we compute its, or we get its corresponding this neighborhood sampler information, that what are its neighbors, what are its selected neighbors at each of the layers, and then we pass it this input to the Triton server. So the 500 basically here is the fixed size which we have fixed while performing the trace on the model. So if you see here, what I did here is that I have set the target node size to be 500, and what it's basically doing is that it's always, whenever it receives the node representation for a particular node, it's always padding it with the rest of the nodes. So only the node which will be at the 0th index, that 256 node will be the node which we will pick, and all the other 499 indexes, the vectors which are at all the other 499 indexes will be the irrelevant. What I'm trying to say here is that let me just, yeah, what I'm trying to say is that, so we are basically making a copy of 500 representations, or 500 node representations of a particular node having this 256 dimension, but the real representation which we will pick is from the 0th index, and all the other 499 values at 499 indexes are useless. So we did this so that in order to make the size of the input remain fixed, which is basically kind of is required by the while we are performing a trace on the model. And yes, so what I was trying to say is that we can just you can just like copy this. You don't need to copy, you can just give while you run the Triton server, you can just give the path. For example, like how you can give the path is that, so here my Triton server is running. So what you can do is that we run the Triton server and we give the path basically to this model repository. So basically this model repository, and it will automatically detect all the models which lies in this folder, and then it will pick those models and then deploy it on the Triton server. Or yeah, it will do this thing for you. So you just need to give this path and you can just start running. Maybe I can, yeah, you can also, there's this, it's mentioned here as well, how you can run the Triton server, basically giving just the path to your model repository. So yes, in this last, so now the trace is being computed and we have arranged our model in a manner which is expected by the Triton server. You can just point out the path to this cloned repository, and then you can just simply start running it on your local machine. So now the next step is that this last one, basically, where we are going to create an application using Triton and Arango database, which will be our Amazon product recommendation application using graph search algorithm. So what, again, run all the necessary libraries, the path to the dataset, performing the sampling, so in this cell, what I'm doing is that I'm creating adjacency for performing a trace. This one is, I basically picked it from here. So I just arranged it in a function so that whenever this function receives the node IDs and their corresponding adjacency list for any target node, what it does is that it gives back you their corresponding Triton acceptable input after performing all the paddings and converting these edge, moving these edge indices to the CUDA device if you're using the CUDA or the CPU, and then it basically returns you the Triton acceptable inputs. So you get basically the 7 inputs here again, and so this cell basically is kind of requirement. So we define each of these 7 inputs using this kind of format, which is basically expected by the Triton server. And similarly, we do it for the output. Since we will receive the node representation at each layer of the graph stage, we are representing it with the list of the 3 variables. So this is the inference method. What this inference method does is that it will receive these inputs, for example, these 7 inputs. And in this method, we will also basically tell the Triton server that these 7 inputs are made for this model, graph embeddings model. And then here we are mentioning the URL where the Triton server is running. And yeah, and then here at the end, we have the model version. And yeah, what this function do is that it receives these 7 inputs, basically the node feature metrics and all the corresponding adjacency list at each of the graph edge layer, and then it converts this 7 inputs into the Triton acceptable format. Basically, we send these inputs as HTTP client, and then it return backs as the response, which is basically the node embeddings at 3 different layers of graph stage. So if we run this, again reading the labels, performing the mapping of the integer labels to the product categories. And if we run this cell, so here again, what I'm doing is that I'm enumerating the test loader, which is basically 1 node at a time. I'm picking 1 node at a time from the test loader, getting its node IDs, corresponding adjacency lists. Node IDs, as I have told you, contains all the nodes involved in the computation when we perform this neighborhood sampling, and the adjacencies are all the edge information at each of this graph edge layer. And then what I'm doing is that for this demonstration purposes, I'm just using the first 5,000 test nodes. So we are just yeah, we are just computing the representations, node representations of the first 5,000 nodes, and then we are storing their layer 3 embeddings. So you can store each of the embeddings at each of the layers, that is at layer 1, layer 2, and graph stage layer 3. But I'm using the layer 3 embeddings and then storing all the embeddings of these 5,000 nodes in a list. So it will take some time, but what for this demo purposes, what I had already done is that I had already stored these representations into my graph database, basically Arango database. So if you, yeah, so this is basically just I'll explain the Arango database parts just like after wrapping up this section basically. So we are just storing all the layer 3 embeddings for each of these 5,000 test nodes. And now what we are doing is that we are creating a connection to Arango database. So our Arango database is running at this URL. We are creating the connection using the credentials and then setting up some lower and upper bounds for the test indexes. So this is the main part here, which I need to explain here. So this is the Arango restore. So as I have in the start of the slides, we have mentioned that there is a dump data set. So what we did is that we have created a dump of Amazon product recommendation data set, which you can directly store inside the Arango database. So what you need to do is that you just need to, so I have also created the order in which you need to run this whole hands-on session. So you need to, for this dump thing, what you need to do is that you need to go into this link, and in this link I have already stored the Amazon product recommendation data set, which you can just restore in the Arango database with this command. So if you use this Arango restore command, and then the server point, the username, server database, and then the input directory, which will be basically when you download this data set, you unzip it, and then you need to give the path of this directory. So what it will do is that it will automatically load this dump into your Arango database. So this is like what I want to show you. So when you restore it, so what it will do is that it will load this database into Arango database. So you can see here that there are again 2.4 million nodes were there in the in this Amazon product dataset. So we are storing each node information as a collection in the database. So for example, this product ID 0 belongs to this. So this is the ground truth, belongs to this home and kitchen class. Similarly, this product ID 9 belongs to this class. And in addition to storing the node information, we are also storing their edge information as well. Basically, which node is connected to which other node. For example, here the node 0 is connected to node 152.857. Okay, so there is this again questions coming. Do you mind sharing the GitHub link? Okay, no problem. Okay, cool. So, yep, yeah, I was. Okay, so I was here. So this basically gives you the edge information. Similarly, if you select this document, it shows that node 0 is connected to this node ID. So basically it stores the edge information. So you can also visualize this graph here in this graph section. So if you click this, so it will basically gives you this very nice representation of the various product IDs connected to each other. So for example, like this highlighting one, it's showing that the product 470 is basically connected to this product ID, this one. So for example, like if you see this one, so this is saying that you can connect this product 470 is connected to 43462 like this, and you can also expand the node to get the to get this more compact graph. And yes, so now the main goal is to, so now we are having the node embeddings for each of the 5,000 test nodes. So now the idea is that we need to, so right now if you see here, so the products are not updated with their corresponding node embeddings or the corresponding predicted category. So what we can do is that now we can basically this cell, basically what it will do is that it will update this graph with the corresponding node embeddings and their predicted product category for each of these 5,000 nodes in the graph. So what we are doing here is that we are adding these two attributes in the graph. So this attributes basically the predicted node embeddings and the predicted product. So this will contains the 47 dimensional node embedding vector from the last layer, and then this will be the products of. So to calculate the predicted product, what I'm doing is that I'm performing the argmax over the last dimension of this vector, and then taking the just taking the product category which is having the maximum probability, and then again just mapping it to the product category. So here we are getting integer, and then I'm mapping it to the product category. And so yeah, so afterwards I am updating the graph with this batch sizes. So you can update the graph with the batch size of 250. So we receive the embeddings and the prediction predicted product category for the 250 nodes, and then we are updating 250 nodes at a time. So this is how the nodes are getting updated. So I had already did that. So if we, maybe I can show you. So if we filter it out, so there's this nice cool feature where you can filter the attributes of a collection. So I know that the product, the first product ID of a test node is 235938. Okay, so if I click this, so it will filter me this ID, and now you can see here is that our graph is updated with these two attributes. So you can say that the ground truth was beauty, and it has predicted it correctly with this beauty product category. And in addition to this one, we are also storing its corresponding third layer embedding. So for this particular node 23598, we are storing its node representation at the third layer of the graph stage. So similarly, we can also store the second layer, its this node ID second layer representation, which will be 256, as well as the first layer as well. So just for this demo purposes, I'm storing this third layer representation. So we will see now what is the benefit of storing these feature vectors in Arango database. So let's see it. So now with this section, we will conclude our hands-on session. So it basically what I will do here, or like what I'm trying to convey here is that our goal of building this application. So what we need to find out is that the products which can be bought together with a query product. So here in this section, we will we will select any query product. So let's say we are selecting this query product 235940. So this is like one of the test node indices. And if we run this cell, what it will return you their corresponding 47-dimensional node representation. It's true label, which basically says that this product ID belongs to this label: clothing, shoes, and jewelry. So this is our query product. So now our goal is to find the products which can be bought together with this query product. So which in simple terms, it means that if you go for a shopping, and if you, with the mindset of selecting or with the mindset of buying the clothes, shoes, or jewelry, then which other likely product you might also be interested to buy with these things. So let's see like how accurate our algorithm is. So this is the AQL query, where what we are doing is that we are selecting our query product, which is basically 235940, and then we are selecting its corresponding feature vector, node representation at the third layer, and then we are calculating the cosine. So this basically the rest of the script basically it's doing is that it's selecting all other. So we are right now we are having 5,000 test nodes which are having their corresponding representations. So we are going to perform the cosine similarity between the query product taken from that 5,000 sampled numbers, and with the rest of the other 4,099 products are also we are calculating with itself, the similarity with itself as well. So if we run this script, which finds the other likely product, and then if we run this, print the results. So here I am sorting the cosine similarities with the highest values. So I'll just explain you in a minute like how the cosine is calculated mathematically, but just let's evaluate or observe the results here. So if you observe the results here, that our query product was clothing, shoes, and jewelry, and the second product which it has calculated with the highest similarity with 99% is that sports and outdoors, which is making basically a sense, because if you want to buy a product related to clothing, shoes, and jewelry, then it is very highly likely chance that you could also buy this product, sports and outdoor product, together with the query product. And let's see if we can find the third highest product. So here you can see a lot of similarity to itself as well, which is a good sign, because it's recommending the same, because like in our data set, in our sampled nodes, we are having multiple products which belongs to this category. So it's good that. Yep, and the third one product which we are getting with the highest similarity is Amazon Fashion, which is also making sense with this query product. And let's see what. So we can see that like the top 2-3 products are making really sense here. So let's see what is the opposite to that, like which is the highly unlikely product. If we can see the similarity, the lowest similarity score. So the lowest similarity which we can find is the cell phones and accessory. So if a people go to buy products related to clothing, buy clothing, shoes and jewelry, so there is this highly likely chance that they will select cell phones, which is also making sense. Also the books, Kindle store, electronics. That's basically a good indicator. So let's just try with one more last changing the query product with another query product. So now this one is the grocery and government food, and we need to do it here as well. 5.9 it is, yeah. And if we do this, and again we run this, let's see which are the products which can be bought together with the grocery and government food. Yeah, and then the second highest similar product is health and personal care. Okay, making sense. And the third one is the home and kitchen, which is also making sense. Health and personal care. Okay, so we can see that the top 3, 4, 5 predictions are really very good predictions or very good similar results. Let's see one last time about the lowest similarity product. Okay. Again, the lowest similarity product is the cell phone and accessory with 36% similarity, and then electronics, video games. That's also making sense, because if you go out for a shopping and then you are aiming for grocery and government food, then there is this very highly likely less chance that you will buy these cell phones or video games, unlike mainly in this case cell phones, unlike you are with your girlfriend, then it could be the case that you will move into this direction. Okay, jokes apart. This one is the last one, basically how we calculate the cosine similarity score. So we basically have their performing the dot product between the feature vectors of the two products, and then we divide by their normalization. So this is how we calculate the cosine similarity. It's just basically you can think of it as an angle in some multi-dimensional space. So if the two vectors are very close to each other, then they will be having a very highly likely cosine similarity score. So yep, so this is all about cosine similarity. And yep, the note here is that for the demo purpose, I'm using the 5,000 test nodes, but definitely if we go for more nodes, results can be improved. And the second one is that there is also a lot of room for improvement of the accuracy of model, which can be achieved using hyperparameter tuning, for example, setting different number of search depth, like k is equals to 3, 4, or 5, or playing with the size of hidden layers, like we have used 256, and you can go for 64 or 128 like this. And another interesting thing to experiment would be to use different neighborhood sampling techniques like random walk. So here in this graph stage algorithm, we have used this this uniform random sampling instead of random walk. Therefore, I can leave this as a homework for you. Okay, that took a pretty much time, which was as expected. So that was all from my side and all the things I want to convey about the role of the graph machine learning, what are its application, and how we can actually write this production in production ready graph machine learning applications by leveraging Arango database and Triton inference server. Thank you for the talk. Oh, you're welcome. Okay, thank you very much, everyone. So in case if you want to contact with me, or if you have any kind of questions, you can always reach me on if you want. I can share my LinkedIn, or I have also written some Medium posts, or you can always like create a issues on this GitHub if you found any kind of difficulty to understand the code or anything related to the graph machine learning. So I'm always happy to help. Thank you very much, everyone, for attending.